Well, from the previous topic, we discussed about monoprotic acid-base equilibrium. And now we will be moving forward into polyprotic acid-base equilibrium. But before that, let me introduce to you our learning objectives and our conceptual framework. Now, we better start our discussion. Before anything else, we must differentiate monoprotic acid-base over polyprotic acid-base. So monoprotic acid is an acid that can donate only one proton, while polyprotic acid can donate more than one proton. Similarly, a monoprotic base can accept one proton, while a polyprotic base can accept more than one proton. The name polyprotic literally means many protons. Polyprotic acids are specific acids that are capable of losing more than a single proton per molecule in acid-base reaction. In other words, acids have more than one ionization H plus atom per molecule. From this table, we see that sulfuric acid is the strongest. It is important to know that K1, K2, K3, where K stands for the acidity constant or acid ionization constant. These constants are used to measure the degree of dissociation of hydrogens in the acid. We have an example, the hydrosulfuric acid. To find K1 of hydrosulfuric acid, we must write first the reaction. Then divide the products by the reactants. To find K2, we are going to start the reaction. Just like when finding K1, we need to write the products over the reactants. From these reactions, we can observe that it takes 2 steps to fully remove the H plus ion. This also means that this reaction will produce 2 equivalence points of stoichiometric points. The equivalence point is the point doing an acid-base titration in which there has been equal amounts of acid and basic solution. This is the graph, and we are able to see exactly just what 2 equivalence points look like. Note that the multiple equivalence points, and notice that they are almost straight lines at that point, indicating equal quantities of acid and base. So now, how to calculate the pH of the solution or a polyprotic acid base? Let's have an example. What is the pH of 0.75 moles of sulfuric acid? This is the equation. Now, we have our ICE table. By the way, ICE stands for initial, charge, and equilibrium. It is a simple matrix formalism that used to simplify the calculation in reversible equilibrium. Let us assume that X in the denominator is negligible. Therefore, X is equal to 0.011 moles. Since we know the value of X, we can use the equation from the ICE table to find the value of HSO4 negative. So HSO4 negative is equal to 0.75 moles minus X. We know that the value of X is 0.011, so we will going to subtract them, and the answer will be 0.75 moles. We can also find H3O plus using the equation from the ICE table. Now we can find the pH from the calculated H3O plus value. So the answer will be 0.119.
Good day everyone, my name is Michael, and today we will going to tackle about polyprotic acids. So what is polyprotic acids? Polyprotic acids are specific acids that are capable of losing more than a single proton per molecule in acid-base reaction. In other words, acids that have more than one ionizable H plus atom per molecule. Protons are lost through several stages, one at each stage. with the first proton being the fastest and most easily lost, contrasts with monoprotic acid in section. So polyprotic acids contain more than 1 mole ionizable hydrogen ions per mole of acids. They ionize to give more than 1 H plus ions per molecules. Possible forms of 3 polyprotic acids are given below after their dissociation in H plus ion. We have here an example for polyprotic acid formula. So first is we have H2S. So second is HS negative, meaning it lost one single proton, and then next is S2 negative, meaning he lost two proton at a time. So that is how polyprotic acids. This acid ionized in several stages, giving out 1 proton at each stage. So the acidity constant for these acids may be written as K1, K2, and K3, or K1 sub 1, K sub 2, or K sub 3.
Good day everyone, my name is Christine Aloy and my topic is all about polyprotic buffers. So many acids donate more than 1 H plus, diprotic acids, and 2 H plus or polyprotic acid. Let's examine diprotic acid. Malonic acid is 2 carbocyclic acid and the first protons comes off with malonic acid placed in water, and then it is the conjugate base from the first step that can release a second proton in the water, and again Ka1 is equal to 1.2 times 10 to the power of negative 3, and then the Ka2 is equal to 2.0 times 10 to the power of negative 6, which is 2 times smaller in Ka1. So what we want to look at it is when malonic acid is just a white crystal powder is placed into water, what species represent? I want to draw species present in solution, and it could be very difficult to put the chemicals structure malonic acid, and so we will go to the weak diprotic acid, this H2A. So 2 protons then dissociates with H plus and label the conjugate base with HA negative. So HA negative of course is the reactant, and then the final conjugate base, the dianion malonate, represent A2 negative. So we are going to place into solution, into aqueous solution, some malonic acid. This is a weak acid and so hardly dissociates at all. Its concentration of 1 molar, we would expect about 95% of the weak acid to remain in solution, and only 5 of the acid dissociates into HA and H+. Now, in calculating the acidity of the solution, we are going to assume that the proton concentration is entirely governed by the first dissociation step. The idea is the second step is small equilibrium constant, and there's very little HA minus in or HA negative in solution. To begin with, all the protons in solutions comes from the first dissociation step. Another observation that the HA negative concentration and the H plus concentration will be equal in our solution, there's a consequence to this equality that we explore. So when the HA negative and H plus are sum, it has an interesting impact on the dianion in solution. So A2 negative is only produced second equilibrium. So the Ka to describe the equilibrium that produces A2 negative and its products and reactants. So HA negative and H plus will be cancelled and A2 negative will be very close to Ka2 for the second. So in the solution, we will expected 2 times 10 to the power of negative 6 molar A2 negative present in very small quantity. That's all. Thank you.